Okay, so we are transitioning. Your algebra review is complete, and you are now algebra experts. We're going to move to the next phase of the course, which is to work and understand the language of functions. So before we get to functions, let's talk about what a relation is. Relation is kind of like a relationship that you think about on a daily basis. So a relation is a machine that makes sets of ordered pairs. So I take something, I put it into this machine, and it creates a pair that includes that first something. So an example would be, y is the brother of x. So in my first column here, I can write things I want to put into the machine, and then I need to be able to pair this input with something else. So John F. Kennedy, for example, could go into the machine, and if I'm going to pair x with its brother, then I could write Robert F. Kennedy. But John F. Kennedy had more than one brother, so if I put him back into the machine, I could get out Ted Kennedy. Okay, so a relation. A machine that creates ordered pairs. A function is a special kind of relation. So a function number one is a machine that creates ordered pairs. The thing that's different about functions is that for every input, there can be at most one output. So if I go back to this slide with the relation, this input, John F. Kennedy, had two outputs. That cannot happen for a function. A function can have at most one output. So y is the birthday of x would be an example of a function, because if I input myself, I can only get out one answer. And I believe you would agree that anybody I put into this machine would only have one answer. Nobody has more than one birthday. Okay, and as far as vocabulary goes, I would say birthday is a function of x. Okay, which means that birthdays, which are the outputs, depend on the inputs, who I plugged into the machine. Now, probably one of the most misunderstood things in the beginning of this course is the notation for functions. And it's unfortunate at times that we do this in mathematics, but we reuse symbols. So this is the notation for a function. Up till now, parentheses have always meant multiplication. In this context, parentheses do not mean multiplication. So this is not f parentheses meaning multiplication times x. And that's a huge point, because there are times where you're going to be tempted to treat it like multiplication, but it's not. Okay? So this is read f of x, or sometimes f at x, and basically means this is my input, and the overall symbol stands for the output when I input this object. In this case, it's a variable, but it could be a number. Okay, so for example, f of 1 would mean the output when the input is 1. Okay, the output with input 1. That's the symbol for it. Now, it could be a numerical answer, obviously, but if we just want to talk about it symbolically, that's how we will do it. Okay, we can sometimes, for example, plug in words into functions, because functions don't have to be necessarily mathematical or numerical, but we could plug in Chevrolet, for example, into our function, whatever our function is going to do. And so what would that mean? That would mean the output with the input of Chevrolet. And you can even plug in expressions into functions. So for example, we could plug in x plus h into a function, and all that would mean, f of x plus h is, what is the output when the input is x plus h? Okay, no big deal. But we got to not think of this as multiplication, because it'd be attempting to distribute the f to the x and to the h, but that's not allowed in general. Now, functions can be expressed at least 4 ways. Okay, you'll see it 4 ways in this course, and they can probably be expressed more than 4 ways. They can be expressed in words. Okay, I gave you an example. Birthday is a function of x. That's just a non-numerical example. You could do several numerical examples in words. So, for example, f is the square of x is another way to define a function with words. Room temperature is a function of time is another way to describe a function using words. You're used to seeing them defined in terms of symbols using an equation. So for example, f of x equals x minus x squared plus 1. So they're telling you this is how you find the values of the function. Whatever the input is, you take the input, subtract the input squared, and you add 1. That's how you get function values. We can define functions with tables, where you put the inputs next to the pair, output that is matched with it, and then we can define functions by graphs. Inputs are generally on the horizontal axis, and outputs are on the vertical axis in most cases. Real quick slide here to talk about the difference between the symbols f of 2 equals 3 versus f of x equals 3. So let's talk about what these mean separately. This means the output of f when the input is 2 is 3. So, in other words, the ordered pair 2, 3 is created by that function. Okay? The second statement is slightly different. This one would say the output of f with input x is 3. So that means no matter what you plug in to this function, okay, you will always get out 3 as an answer. So 2, 3, 4, 3, 7, 3. These two symbols mean totally different things. This one says that your function value is always 3, regardless of what you input. This one says that your function value is 3 when the input is specifically 2. Some people like mental pictures of what a function is, so here they are. If we think of these blue cylinders as our function machines, we take our inputs, they go into the machine, and when they come out, they are something different, and we call the output f of the input. At times with a function, something can go in, but nothing will come out. That's when we say a function is undefined somewhere. And then a picture that's not a function, but is a relation, is when one thing comes in and multiple things can come out. Just so you have an example of a numerical example of a relation. So I could say y is an equivalent fraction to x. So if my x was 1/2 and it went into a function, or it went into this relation, I should say, it's not a function, because you're going to see here in a second, multiple things can come out. Okay, well, what could come out? Well, what's an equivalent fraction to 1/2? Well, you could get out 2/4, right? That's an equivalent fraction to 1/2. And you could get out 3/6. That's an equivalent fraction to 1/2. And there's lots of others. So you can see that this relation is not a function, because when I plug in one thing, multiple things could come out. So there are mathematical examples of relations, not just the ones verbally that I gave earlier. Okay, some vocabulary with functions. So the input we call the independent variable, because I get to choose the inputs. I get to choose what I want to place into the machine. What comes out is dependent on what gets put in. So generally speaking, we use the x variable to stand for the inputs. So the x is the independent variable, and y, the output, is the dependent variable. Now, the set of numbers, or the set of all possible things that are allowed to go into the function, we call the domain. So sometimes you'll have a function where certain things can't go in. In other words, if I put this thing in, nothing will come out. So that number would not be in the domain. The set of numbers that come out of the function is called the range, the set of all possible outputs for the function. In pre-cal, range is a trickier idea to determine. We're going to mainly focus on domain in this course. For now, there are only two main mathematical restrictions on a function's domain. Okay? Two things we cannot do at this point in the course. We can't take the even roots of negative numbers. So for example, we know that the square root of -2 is not a real number. So if our function produced that, then that number would not be in the domain. And then we are not allowed to divide by 0. So those are the two restrictions we have at the moment. As the year goes on, you'll see some more restrictions be added on to a function's domain. Range, unless we give you a graph at the moment, is out of our reach for now. Okay, sometimes functions have to be defined in pieces, which means that I have a function that's really several functions whose domains are different. So for example, this function h has 3 pieces to it. This first piece has domain only when x is less than 4. This second piece has a domain only when x is 4. And the last piece has a domain when x is bigger than 4. And when we have a piecewise function, obviously these domains can't overlap, or we'd no longer have a function. So if I want to use a number line example, this function h would be equal to x minus 1 on this portion of the number line. This function would be equal to -5 only at this one dot on the number line. And then the function h is x squared plus 4 for the rest of the number line. You'll see quite a few piecewise functions as the year goes on. The main thing is, if you're asked to find function values, you just ask yourself, which part of the domain does my input lie in, and then that's which rule I'll use. So for example, if I'm asked to find h of 3, I look and I ask myself, okay, is 3 bigger than 4? No. Is 3 less than 4? Yes. So I would use the rule x minus 1 to determine the function value. Similarly, if I wanted to find h of 10, since 10 is bigger than 4, then I would use this rule here to determine the function value. And so I would use 10 squared plus 3. Okay, and then the last thing I want to talk about as far as algebra functions is that sometimes we're going to do problems where we're not going to be told what the rule for the function is. In other words, what's the equation? We're just going to do algebra with the notation for functions. So here's an example from a past AP exam where there's only pre-cal involved. Okay, it says let f be a function with domain the set of all real numbers. So that means I can input anything I want into my function f. Okay, so inputs, I'll say all inputs are allowed. And they tell you that this property is true for this function f. Okay, this is not true in general, but for this function, f of x plus y, in other words, if I input a sum of two numbers into the function, it's the same thing as the function at the first number times the function at the second number. That's not true in general, but for this function it is. Okay? Now, given that f of 1 is 2, generate some other function values. So what the heck can we do? All we know is that f of 1 is 2, and we have this property here. So in this first piece, I have to be able to input two numbers, x and y. I can choose whatever I want them to be. And I'm in charge. That's the input. That's the independent variable. I can choose that. So since I know f of 1 is 2, maybe I'll use 1 for both x and y. So if I do that, I get f of 1 equals, f of 1 plus 1, which would really be f of 2 when I'm done, will be what? F of the first thing, which is f of 1, times f of the second thing, which is also f of 1. And since f of 1 is 2, I get 2 times 2. So f of 2 is 4. Let's do another number here. Okay, now that we know f of 1 and f of 2, let's do f of 1 plus 2. also known as f of 3. So by the rule, this would be f of 1 times f of 2. So f of 3 would be equal to 2 times 4, or 8. And let's find one more. Let's find f of 0. Okay. So how would we do f of 0? Well, I know f of 1. So if I do f of 0 plus 1, that's the same thing as f of 0 times f of 1, based on the property that this function has. Okay, this is f of 1, and we were told f of 1 is 2. So 2 is equal to f of 0 times f of 1, which is also 2. If we divide both sides by 2, then we can determine f of 0 is 1. Okay, so without knowing the equations, or the function's equation, we're able to use the properties that were given to determine some more function values. You'll get problems like this from time to time and have to deal with the notation, the symbols of functions, and not necessarily know the rule for the function. Okay, I told you functions could be represented by tables. So here is a horizontal table where the inputs are above the outputs, and here's a vertical table where the inputs are next to the outputs. One of these is a function, one of these is a relation that's not a function. Let's see if we can determine which is which. So remember that a function can have one input, have only one output. So for example, I see that 2 is repeated in this table. It's the only number that's repeated. So if 2 is repeated in the table, then it has to have the same output both times. So here you see 2, 4, and here you see 2, 2. So this one is not a function. This is a relation that's not a function. Notice that there are several occurrences of the same output. Circle those in blue here. So 4 is an output, 4 is an output, 4 is an output, 4 is an output, 4 is an output. And there are several inputs that have the same output. That's allowed. Okay, that's allowed. But when you have the same input, they must have the same output. Down here in the second table, you'll notice that 1 is input twice. And if 1 is input twice, you must get the same output both times. And we do. Okay, so based on what I see in the table, this table represents a function. Again, there are multiple occurrences of the same output for different inputs. That's okay, but you can't have one output have more than one input. What that means from a graphical perspective, okay, is that if you have one input, which remember inputs are placed on the horizontal axis, then you can only have one output. So wherever there's one x value, you can only have one y that goes with it. So for example, when x is -1 on this red graph, you'll notice that there's a y value here and a y value here, which means this graph is not the graph of a function. It's a relation, but not a function. And there are several other x values where that graph fails to be a function. Okay? In general, we say the graph of a function must pass a vertical line test, which means if I place a vertical line anywhere on the function's graph, that vertical line can only cross the graph once. You can see there's many places where this graph is going to fail the vertical line test, not a function. If I come over here and I move this vertical line across this graph, the line only crosses the graph one time for each x value. Okay, so this graph would be an example of a function. And again, I may not know the equation for the function. That's not the point. The point is this graph does determine a function.